The first of our speakers of today will be Igor Ermakov, which is going to speak about almost complete revivals in quantum algorithms. So if you please can unmute your microphone.
Okay, hello everyone. My name is Igor Yermakov and welcome to my flash presentation. So what happens if you put a pure state qubit inside a random infinite temperature reservoir, as in the picture? Our intuition is that it will quickly relax to the equilibrium value of the reservoir as it practically becomes part of it. Are there any deviations from this rule? Yes, plenty of physical mechanisms of unusual equilibration, such as integrability, glass systems, MBL, you name it. Yet the most well-known examples are associated with properties of a particular Hamiltonian. You can move your attention, however, from Hamiltonians to special tuned initial states. Our paper states that for every Hamiltonian, there are such initial states that for selected local observable and predetermined moment of time, this observable exhibits an almost complete revival to its initial value. Summarizing, arbitrary Hamiltonian, arbitrary predetermined moment of time, special finely tuned initial states. Works for both thermodynamic limit and for quantum systems of a few qubits. While this effect is in general important for current discussion in formalization, we also suggest that it can be used for benchmarking of quantum simulators because it allows to prove that the target state was reached successfully by doing only single measurement of local observable instead of complete tomography of state, which is in case of many-body systems is not available. We also propose the conception of delayed disclosure of secret, which we think is important for information theory. And imagine if you encode in this initial state a bit of information, and you can access it only at the revival time, and any attempt to access it before revival time will destroy this information forever. So thank you for your attention, and feel free to contact me for questions or if you just want to chat or whatever.
Fantastic. Thank you, Igor. Let's move to our next speaker, who is Isidoro Gonzalez, which is going to talk about using magnetic domains as an accelerator for out of equilibrium critical dynamics.
Okay, hello, everything is okay? You can...
Yes, we can hear you. Please
okay.
Go ahead.
Okay, so thank you. I'm going to talk very fast, sorry, but the main idea of this work is that equilibrate a system at some target temperatures could be very difficult. In particular, if you have a continuum of time scales, which is typically in a second order phase transition, it could be harder. However, if you develop a smart way to equilibrate the system, you can obtain in principle exponential speed up, for example, for this relaxation process. In particular, in your study, we consider the two-dimension Ising model, which have a phase transition between a paramagnetic phase and a ferromagnetic phase. And we want to equilibrate the system in a target temperature in the paramagnetic phase, really close to the critical temperature, as you can see in this picture. The unexpected result which we have found is that pre-cool the system can give you this speed up. So we have a two-step protocol. We first put the system in the ferromagnetic phase. When the typical size of these magnetic domains reach some target value, which is given by the model and the target temperature, we change the thermal bath temperature. And this gives you a very, very faster relaxation, which is very unexpected. And remember a little bit to the Pemba effect, where hotter system can cool faster than other. And this is all. If you want to see all the result, it's available in this link in the archive, which I have sent to the chat, or scanning the QR code and see you if someone have any question in the break rooms. So thank you for your attention.
Fantastic. Fantastic, Isidoro. Thank you very much. So our next speaker, Teja KMB, is going to talk about thermodynamic information erasure with computational limitations.
So today I will be talking about this problem we have been recently thinking about, which goes as follows. Given access to a limited number of gates, how many erasures do you need to reset the system? So you can see it in the circuit. It goes like you start with row, apply the unitary UR, which is constituted of at most R gates, and then you apply Landover erasures represented by box else, so that you get somewhere close to the zero state. So why are we actually interested in this question? The basic point is there is a recent interest in connecting complexity to physics. And we feel like this is a very good starting point in that. In order to do that, we worked out and studied a new complexity, a new entropy, which we call complexity effective entropy. And as it turns out, the number of erasures needed is precisely quantified by this quantity. And this entropy also has very nice properties, like we could establish a complexity cost and work cost trade-off, which is quite cool. As in, if I am given access to more gates, I can get away with performing less erasures. I'm considering that for each Landover erasure, I need to pay KTL into energy and all that thing. So at the core of it, I would like to say that universe can do everything, but we know not. And the new entropy, which we call complexity effective entropy, takes this into consideration and quantifies how much we can do. Time. Yeah, I would, if anybody is interested, you can contact me or any of my co-authors and look for, you can also look into my master's thesis, which should be out in a month or so. Yeah, thank you.
Thank you, Teja. Thank you very much. We can now move to the talk by Alexander Teretekov, who is going to talk about quantum thermodynamics of slow observables. So Alexander, please.
I consider the usual canonical Gibbs state with the Hamiltonian of the form pre-Hamiltonian plus perturbation. I assume that I have access only to very special class of time-dependent observables, which are in resonance with the pre-Hamiltonian. This is a usual situation in the case of spectroscopy, for example. I consider the long time scale with respect to this free Hamiltonian such that fast oscillations could be neglected and only slow observables could be actually observed. In this situation, the usual Gibbs state is equivalent to the one obtained by this averaging projector P, and I call this projected Gibbs state an effective one for slow observables. I represent it in the Gibbs-like form with the effective Hamiltonian. It could be obtained by cumulant expansion, and usually such a representation is better from the point of view of the convergence rate of the perturbation theory. There are several initial terms of the perturbation series. The first plus the second one is nothing else but the rotating wave approximation. And this is similar to most approaches when the dynamical effective Hamiltonian arises. And the third one is a temperature-dependent contribution, which I regard as the first non-trivial one. I think such an effective Gibbs state could be applied to many long time scale calculations, for example, to calculation of the stationary states for perturbatively obtained master equations. So that is all. Thank you for your attention.
Thank you very much, Alexander. We now move to the talk by Varun Narasimhashar, who is going to talk about thermodynamic resources in continued variable quantum systems. Please go ahead.
Thank you. So the main ingredient in our work is the schematic that you see in the top center panel. And what this describes is a simple sort of information theoretic way of formulating thermodynamic processes on continuous variable bosonic systems. Namely, we have incoming modes that are mixed with thermal modes at some background temperature using passive linear optic or bosonic circuits. And then we are allowed to discard some of the modes And if we look at the kind of transformations that occur from the incoming to the outgoing modes, we can recover some trends that resemble the second law of thermodynamics in some sense. So if you focus on the bottom left diagram, there is a schematic depiction of something that we can call effective mode temperatures. And what these are is if you take some state of several bosonic modes and you allow any possible linear optic rotation of those modes, and then you choose a rotation such that you isolate one mode that is locally has the highest covariance variance in phase space. You can think of that as the hottest mode, and then as you can sequentially isolate the second hottest mode, third hottest, and so on. And we can show that the temperatures that are, or the effective temperatures defined by these this sequence follow a thermalization like law, where they all converge towards the temperature of the bath when you apply a process depicted by the schematic on the top. In addition to these, we have what you can see on the bottom right. I'm sorry about the size of the graphic there, but essentially what we have is a deterioration of signal to noise ratio in phase space displacement, meaning that if you think of the representation of the bosonic state in phase space as a medium for encoding information, then the usefulness of this medium only deteriorates under the operations given by the top panel. And this
Varun, I'm sorry, but you need to finish soon.
Okay. Yeah. So you can find more details in our paper, which is in the chat. And thank you for your attention.
Thank you very much, Varun. So our next speaker is going to be Vivek Badandi, and he is going to speak about minimal two-body quantum absorption refrigeration. Please go ahead.
Thank you. I'm Vivek Bandari, and I'm from University of Rochester. So this was the work done with Professor Andrew Jordan at Rochester, and we studied two minimal two-body quantum absorption refrigerator. So there were two basic things that we thought were missing, because in this literature, because there were like a lot of works on two-body refrigerators and what is the minimal setup to have the refrigerator, and what are the effects of going beyond the Bohm approximation, that is strong coupling, towards the refrigeration. So to understand that, what we did was that we took two qubits and we tried to find out a possibility to have refrigeration in this kind of system, where S1 is one qubit and S2 is another qubit. So we were able to find refrigeration with just two qubits, and we say that is the minimal setup for obtaining refrigeration in this kind of devices. And then we move on to study what is the effect of multiple levels by taking coupled nonlinear resonators. And we see that in some parameter regime, having multiple labels is better than having two qubits. We used two different formulations. One was Master equations, and other was Keldysh non-equilibrium Green's function. And by going beyond Master equation, we could also include beyond Bohm approximation, and we could study the effect of strong coupling. And in this plot, you can see strong coupling deteriorates the cooling effect. So if we just stay in the Bohm approximation and take weak coupling limit, there might be a reason to believe that we are getting a huge cooling effect. But on the other side, if you take other terms into account, the cooling is drastically reduced. So the results are like there are better cooling effect in multi-level system compared to qubits. We observed that ZZ coupling between the qubits gave better cooling compared to the XX coupling, and strong system bath coupling was not didn't help in cooling. It reduced the cooling effect. Thank you.
Thank you very much, Vivek. We can now move to the next speaker, Alejandro Pozas, who is going to speak about quantum atom engine with finite heat bath, energy correlations, and degradation.
All right. So, hi, everyone. Well, by now, you probably all of you know that classical equilibrium thermodynamics is grounded in assumptions that involve infinity, typically. You have infinitely weak interactions that must last for an infinite amount of time. And then there is this notion of infinitely large systems that are called thermal baths. And well, these assumptions hardly, if at all, hold when we deal with interacting quantum systems. In order to alleviate the issues that arise when considering the thermodynamics of interacting quantum systems, in the work that I'm presenting, we restrict to Gaussian states and operations. These states and operations are useful in this context because they admit a description that is efficient in the system size, and this allows for an exact solution of the dynamics. Therefore, we consider interactions between working mediums and baths, all composed of coupled harmonic oscillators, initially set in thermal states at some specific temperatures, and undergoing interactions that are described by quadratic Hamiltonians. An example that we put in the paper is the study of thermal engines undergoing Otto cycles. And there we focus in understanding how the relevant figures of the cycles are impacted by the finite size of the baths and by the finite strength and timescales of the interactions involved. For instance, the work output of the engine as a function of the operation time is in the top right figure. More interestingly, we also analyze the correlations that build up between the working medium and the baths. This is the figure at the bottom right, which shows that the correlations generated by the interactions spread through the baths as time goes on. But probably the most interesting feature that we can study is that our approach allows to consider the dynamics from the point of view of the baths themselves. We can thus explore quantities such as the correlations between the baths. And in fact, we find that these correlations have a very strong impact in the workings of the engine and its efficiency. We believe that this work not only will help in the efficient modeling of experiments, but that taking the standpoint of the baths opens up a very interesting research avenue. So if you're interested in knowing more, feel free to take a look at the paper. The reference is down in the left, or just drop me an email. Thank you very much.
Thank you, Alex. Let's now move to the talk by Nathan Myers, who is going to speak about quantum auto engines and relativistic energies.
So the idea of using relativistic phenomena as a source of power has long been a staple of popular science fiction, such as the matter-antimatter reactors that power the warp drives of Star Trek. However, with the discovery of Dirac materials, systems whose low energy excitations behave like massless relativistic particles, along with methods of simulating Dirac dynamics in ion trap systems and microwave resonators, relativistic quantum engines are no longer solely the realm of science fiction, but actually accessible at laboratory scale energies. Relativistic quantum systems play host to phenomena that aren't seen at lower energies, such as the existence of both particles and antiparticles, restrictions on the dynamics due to the light cone, and a linear rather than quadratic dependence on momentum, leading to a much broader momentum distribution, which I've illustrated here on the far left plot. So this opens the question of what impact do these phenomena have on the performance of a quantum heat engine? How does the power output and efficiency compare to the classical non-relativistic case? So is Captain Kirk making the best choice for running the Enterprise? So a quick teaser for the results. We find that the interplay between these relativistic features leads to enhanced work output, but at the cost of significantly smaller efficiency. And for the full details on the analysis and the interpretation, manuscript should be available on the archive soon, and I'm also happy to discuss more or answer any questions afterwards. Thank you.
Great, thank you, Nathan. So with this, we can now move to the very last speaker of the flash presentation, who is Sadek Saleh, and he's going to speak about heat transport in overdamped quantum system. Please.
Hello, thank you very much. So I'm going to talk about heat transfer in quantum overdamped systems, and our system of interest is two magnetic coupled RC circuits, and we are looking for the heat currents when the coupling between the system and the bath is really strong, which we call overdamped. So the two resistors at each ends of the two circuits, they're representative of the two heat baths with different temperatures, and the two systems in between are nothing more than two harmonic oscillators, represented by two LC circuits. We can quantize this system and then write the Hamiltonian as it's written there. And then for a steady state heat currents, we say that the amount of heat that is dumped by the first resistor on the left, for instance, is equal to the amount of the current that goes to the right resistor on the right, which has different temperature to the system. So by finding the time evolution of the covariance matrix of the system, we can find the heat currents, which is dependent on the two temperatures of the two heat paths. And what we are looking for is the analytical expression for the heat current in the overdamped regime, where the condition is given by when we say that damping frequency, I said that system is just two damped harmonic oscillator, but damping frequency gamma is much larger than the natural frequency of the system and the thermal frequency. So in this way, we can divide the heat currents into two classical and quantum contributions and find them analytically. And then the overdamped condition gives us three different temperature regimes, where the high temperature regime is irrelevant to our problem because in that regime, the thermal frequency is much larger than the other relevant frequencies. But the two other frequency regimes, intermediate temperature and low temperature regime, where for the low temperature, we have the damping frequency is much larger than the omega plus minus, which is the natural frequency of the system in the overdamped regime. And we can see that the heat currents are only quantum. So the quantum contribution only remains in there. And for the intermediate temperature, we can see that the thermal frequency lies in between the two other relevant frequencies, where because the thermal frequency is much larger than the natural frequency of the system in the overdamped regime, we expect that only classical contributions were survivable. However, we can see some non-vanishing quantum contribution to the heat currents, even for larger temperature with respect to the natural frequency of the system. Thank you very much. I can just send the link to the chat if anybody is interested.
Fantastic. Thank you very much. So with this, we can conclude the flash session, and let me thank all of the speakers for the talks. And as I say, please do engage with them in the Slack channel.